What does reduction in area mean for material ductility? Imagine bending a piece of metal until it almost breaks. Now, think about what happens right before it snaps. That's where reduction in area comes into play. It's a way to measure how much a material can stretch and deform locally before it finally fractures. When you pull on a material, it doesn't just stretch evenly. It often forms a narrow neck right before breaking. The reduction in area tells us how much that neck has thinned out compared to the original size. This measurement is expressed as a percentage. For example, if a metal starts with a cross-sectional area of 10 square millimeters and narrows down to 5 square millimeters at the fracture point, the reduction in area is 50%. A higher percentage means the material can undergo more localized deformation before failure. That's what we call good ductility. It shows the material can absorb more energy and stretch more without cracking suddenly. Ductility itself is about how much a material can change shape without breaking. It's usually measured by how far it stretches lengthwise, called elongation, and how much the cross-section shrinks at the fracture point, which is the reduction in area. While elongation looks at overall stretching, reduction in area focuses on that tiny, critical narrowing right before the break. It's a more precise way to see how a material handles stress at the very end of its deformation. When a material has a high reduction in area, it means it can absorb a lot of energy and deform extensively. This helps prevent sudden, brittle failures, especially in parts like pipelines or car components that need to bend or stretch under pressure. On the other hand, if the reduction in area is low, the material is less ductile. It's more likely to crack or break suddenly when stressed, which can lead to catastrophic failure. Understanding reduction in area helps engineers predict how materials will behave in real-world situations. It shows how well a material can handle strain through mechanisms like dislocation movement at the microstructural level. This knowledge guides the selection of materials that can withstand overloads and avoid unexpected failures. By knowing how much a material can thin out before breaking, we can design safer, more reliable products. In essence, reduction in area is a clear indicator of ductility. It reveals how much a material can deform locally before it fractures. This helps us understand how materials will perform under tensile stress and guides us in creating components that resist failure through controlled deformation rather than sudden breakage.